Maybe I'm a crazy person, but I don't trust these Silicon Valley developer elites who shove down their well-crafted and optimized codes down our throats. I think the time to resist has finally come. From now on, I refuse to use their spyware they call operating systems. And in its place will be my own operating system. They want us to be dependent, so they tell us we can't do it. But they're liars! They want us to stay their minions, but we will refuse. So let's stand up and fight for our freedom. Listen, we will develop our own kernel, but it will be some work, and it can't be done in only this video. But nevertheless, we'll have a super minimalistic kernel that prints letters to the screen. It's our first step into freedom. And after that, we only have to do a million other things to get a running kernel. And when we're done, our kernel is probably not performant, likely unstable and insecure, but we're free. Alright, let's dive in. But before we start developing, shouldn't we educate ourselves about what a kernel is and what it does? Answer: yes. So, to put it simply, the kernel tells the hardware what to do. And we can give some examples to make this more tangible. So one would be that it tells the CPU what process to run, and another could be that it decides where in memory data is stored, and the last one, that it talks to devices like the keyboard. I don't know if you noticed, but this schematic is somewhat misleading. Because, for example, the kernel itself lives in memory, and the CPU is displayed in this corner, even though it's a central hub where everything goes through. Ultimately, what it comes down to is it's all quite complex and kind of impossible to display accurately. And I'd even go further and say that knowing each detail is impossible. But I also think that's not really necessary. So for now, let's focus on a few simple things, and that is the kernel provides instructions that the CPU executes, and there are ways to display letters on the screen, and there are also ways to receive input. Okay, enough talking. Let's do something. So first, we install all the tools we need for developing, and that's some build tools, a bootloader, and an emulator. Alright, then let's briefly talk about how we can use these tools to build our kernel. Our kernel, or any operating system for that matter, is started by going through a boot process. And here's how that basically goes. So after the computer is turned on, the CPU jumps to a fixed memory location. And in that location lives the BIOS. So the BIOS then runs some tests, looks for a bootloader, and transfers control to it. And the bootloader then looks for our kernel, loads it into memory, and jumps to its entry point. And what we have to provide to run our kernel is a bootloader and a kernel binary. And as we've seen in the installs, we use grub as a bootloader. So we then pack grub and our kernel into a bootable ISO file. And once we have that, we can use an emulator to boot from this ISO file. And we already installed an emulator, namely Bochs. Moving on, let's configure Bochs. And yes, you're right, I don't use Vim. And if you don't like that, go fuck yourself. So we give our machine 32 megs of RAM. We don't need a huge amount, but it shouldn't be too little, right? Next, we have to provide a display library, a BIOS, and a VGA BIOS. And for me, it was a little bit of trial and error to get this running. But yeah, that's just how it is sometimes. So for example, I had to use the legacy BIOS because for whatever reason, the other one doesn't work. Next, we tell Bochs to boot from our ISO file and we just pick some name in advance. Then we give our log file a name and configure the CPU. So we use just one CPU and 10 million instructions per second. And finally, we configure some additional debug behaviors that are not super important right now. Okay then. So to be able to build the ISO, we first have to create a specific folder structure. So we make a folder called ISO and within that we make a folder called boot, and lastly within that we make a folder called grub. And in the grub folder we put a grub config file. In the config file we define the menu entries that are shown and where the kernel binary lives, and let's again choose some name and location in advance. And now finally we can start to work on our kernel binary. As a first step, we have to define the memory layout of the binary. And like before, we have to follow some rules such that grub can work with our file. And this diagram is meant to illustrate the memory layout of our binary. And as you see, we have 6 sections. The first section starts at address 0 and goes up to 1 megabyte. And this is reserved space. We cannot put anything in this area. It's like the CPU's personal workspace, but still we'll use it later. In the second section, we put the so-called multi-boot header. And in this header, our kernel basically tells grub how to start it. Next, we have the .text section. And this is where our actual kernel code goes. Then we have a section for read-only data, which is usually for things like string constants and stuff. Then we have a section for initialized variables. And finally, a section for uninitialized variables. And we will use this last section later for our kernel stack. And as a side note, don't be confused about the addresses I've chosen here. Except for the reserved section, these are random example values, which will certainly be different in the real file. Alright, so that's the memory layout. Let's implement it. So the layout is defined in a linker file, so let's create one. Here we go. Before we implement the file layout, we define the entry point, which tells the bootloader where to jump after it's done. So this is a first code that's executed after the bootloader is done. And here we just enter a function name and define the function later. And then we'll just write down the file layout we discussed earlier. Okay, great. Now that we have the file layout, we can fill it with code. And to do that, we create an assembly file. In this file, we first write the multi-boot header and put it into memory. That's just predefined stuff we can find on the internet. Next, we write our loader function, and we already made it globally available. And all it does for now is to write the value into the EAX register and then enter an infinite loop. And that's useful because we can check that everything works. And now, the moment we all waited for, the first test of our kernel. But to be able to start it, we must first compile the assembly file. Next, we use a linker to build the kernel binary, and then we use grub to build the ISO file. And then finally, we can run the ISO in the emulator. Remember that we already configured Bochs to use this ISO file. Alright, no errors, so that's good. Bochs shows nothing on the screen, but that's what we expect because we didn't write anything to be displayed. But let's take a look at the log file. So if we scroll down, we see that the EAX register contains our value. And this little step, to me, is already so cool. And as a little side note, we can also mount the ISO and inspect it. And this is also so nice to see. Alright, because we like our mental health, or what's left of it, we don't want to write the entire kernel in assembly. So we need a way to write and use C code. On the surface, that seems not to be very difficult because we can simply call functions from the loader function in the assembly file. But there's a little problem. Function calls require a stack. So before we can implement any function calls, we need to set up a kernel stack. But lucky us, that's not very difficult. Okay then, let's briefly talk about how to set up the stack. If you remember, I already mentioned that we put the stack in the BSS section. So to set up the stack, we first reserve some memory in BSS. And as its size, we just choose 4 kilobytes. This doesn't really matter, we can change it later. And to initialize the stack, we only have to set the stack pointer to the beginning of the reserved region. And then we can use the push instruction to push values on the stack, and the stack pointer then increases automatically. And of course, we can also pop values where the stack pointer decreases automatically. And to understand why we need the stack for function calls, let's also briefly talk about function calling conventions. And let's do only a very simple example of a call and then move on. Let's say we want to call a function with 3 arguments. Then the convention requires that we push each argument onto the stack in the opposite order. After we push the arguments on the stack, we call the function, and the call then also pushes the return address on the stack and maybe some other stuff. Okay then, we're ready for implementing. First, let's create a C file and write a test function. And let's use a very simple function that just adds some values and returns the sum of the values. Next, in the loader file, we have to call the function and we have to push the function arguments on the stack. Now, let's set up the stack. And to do that, we first define the stack's size, and as I said, for now we choose 4 kilobytes, and then we reserve some memory of this size in the BSS section. Because the stack grows downwards, we set the stack pointer to the top of this memory region. And because we pushed some values onto the stack and thereby changed the stack pointer, we have to clean up a little bit by resetting the stack pointer to the top of the stack. Before we test the function call, let's write a makefile to make the compilation process a little more convenient. Okay then, let's compile and run the kernel. Again, nothing is displayed, which is expected, and to check if everything worked, we have to take a look at the function's return value. And the calling convention says that a function's return value is stored in the EAX register, so we have to take a look at the logs again. And indeed, EAX contains the right value. Now that we can use C to code, let's try to display something on the screen. And to do that, we use the so-called Framebuffer. The Framebuffer is a memory region within the reserved section we already talked about. To display something on the screen, we can write entries with a specific structure into this region. These entries are continuously read by the hardware and transformed to output on the screen. And as a starting point, we use the text mode Framebuffer, which, as the name indicates, can only display text. Later, we'll switch to the pixel-based Framebuffer, which is more versatile. Alright, let's take a closer look. So the Framebuffer is located at this fixed address and has a size of about 32 kilobytes. Now, the idea behind the text-based Framebuffer is to divide the screen into 80 columns and 25 rows. And each entry in the Framebuffer then fills one of these cells with a letter. Okay, let's take a closer look at how this works. So each entry has a size of 2 bytes, which is 16 bits. These first 4 bits define the background color, these 4 bits define the text color, and these 8 bits define the letter to be displayed. And this example is the letter X in green and a white background. Now, if we write this value at the beginning of the Framebuffer, it is displayed in column 1 and row 1. If we then write this value again, it is displayed in column 1, row 2. And if we keep going like this, all the cells will be filled one by one until the screen is entirely filled. And what's worth noting here is that if we fill the entire screen, we've only used 4 of the 32 kilobytes. This means we can write beyond what the screen is able to display. And we will come back to that when we introduce scrolling. Okay, first let's create a file for types and add all the colors we can display. Additionally, let's add some type defs which make it easier to see the bit length of variables. Next, we delete the test function and replace it with a function that writes entries to the Framebuffer. And as arguments, the function takes an ASCII letter, a row, a column, a text color, and a background color. Based on these arguments, the function first constructs the entry, so we construct a 16-bit value where we have to shift our letter, text color, and background color to the right positions, and then second, we write the entry to the correct location in the frame buffer, which is calculated from the row and the column values. We also add a main function for the kernel, which will be the function we call from the loader file. And to test our Framebuffer function, we write a loop that fills the screen with the letter X in green and a white background. Okay, let's change the loader file such that kernel main is called. And we also create a new folder which will contain our header files. And let's not forget to add that to our make file. Alright, we are ready again to do some testing. So let's compile and run Bochs. And it seems to be working, but that flickering isn't normal. If we investigate a little, we see that Bochs is running too fast. And that's not an issue if I run Bochs directly on my host machine, but here I run Bochs in another VM. So one solution is that we edit the Bochs config like this, which apparently fixes the timing issue, but the flickering is still there. I also played around with a VM configs a little bit, but the issue still persists. So we solved the problem by using another emulator. So let's install it and run it. And lucky us, this looks better. So the problem is solved, I guess. Before we continue, let's tidy up a bit. First, we move the colors to another header file that we'll use for I/O stuff. And let's also put a function declaration for our Framebuffer function in this header file. Then we can also move the Framebuffer function to a separate C file. All what's left to do now is to modify the make file such that it takes our changes into account. A quick test and it works like before. Perfect. Alright then. Let's continue with moving the cursor and scrolling. To move the cursor or scroll up and down, we send certain commands to the CRT controller. The CRT controller is a chip which manages how text is rendered on the screen. And it has several registers to control, for example, the cursor position, the cursor shape, or the display offset. To access these registers, we have two ports. We have the command port and the data port. So the command port takes the index of the register we want to access, and then the data port takes the value we want to write to that register. And to do that, we can use the CPU's out instruction. Now, let's take a closer look at moving the cursor. Suppose we want to move the cursor in row 2, column 5. Then the cursor offset is 2 times 80 plus 5, which equals 165, and converted to hexadecimal, we get this value. But because the data port is only 8 bits wide and we need to write 16 bits, we have to split the value and send the high and low bytes separately. And to do that, we first send the index of the cursor position high byte register to the command port and then the high byte value to the data port. The controller then automatically writes the value to the register. Next, we do the same with the cursor position low byte register and the corresponding value. And that's it. We moved the cursor. And scrolling works exactly the same. Say we want to scroll down 3 lines. The offset then is 3 times 80, which equals 240 and looks like this in hex. And then we use the same method as before to write the values to the proper registers. And again, that's all it takes. Alright, let's remove the letters for a moment. And then we test moving the cursor in assembly first. And to use the out instruction, we have to move the command port address to the DX register and then the high byte index into AL. The out instruction then sends the data and thereby tells the CRT controller that we want to access the high byte register. Next, we send the value. Again, we have to move the data port address to DX and our value to AL and call the out instruction. And we do the same with a low byte. And if we test this, we indeed see that the cursor has moved. Now, let's also briefly test scrolling. To do that, we bring back the letters and change the registers. And that's all we have to do. So let's test again. And again, we see it works. Okay then, let's implement that in C. First, let's delete the assembly code and then we write a C function that does exactly the same. So the function simply takes a port and the value as its arguments and then executes the CPU instructions we have seen before. And for later use, we also briefly write a function that reads a byte from a port. Next, we define all the ports and values we need in the I/O header file, and then we write a function that moves the cursor to a given position. And in the function, we just set the ports and values as we did before. We quickly add the function declaration to the header file, and then we can test the function. And lucky us, this works just perfect. Next, we also add a function for scrolling. And to do that, we again just set the ports and values as we did in assembly. Then add the function declaration and we can test it. And it also works. Perfect. Alright, we're now at a point where we can start to write some higher level functions that make our lives a little easier. We start with a function that writes strings to the screen. And that's pretty easy now because we can build on functions we've already written. And because we cannot use the standard libraries, whenever we need a standard function, we have to write it ourselves. And for the write to the screen function, we need a Sterling function, so we quickly write one. Then we modify the makefile a little, and now we're ready for testing. So we write a test string and try to print it on the screen. And again, it just works perfect. Okay then, we're almost at the end of part 1. So let's finish up with some more useful functions. First, we write a tiny print to the screen function. Second, a function that prints a byte as zeros and ones, and that's sometimes quite useful for debugging. And finally, a function to style the cursor. And cursor styling works exactly like moving the cursor, except that we use different commands. So with this function, we can make the cursor big or small, and we can disable or enable it. And next, we add the function declarations and modify the makefile once more. Okay then, let's test all of it. First, we print the number 18 in binary form, and this looks good. The letter printing also looks fine. And finally, the different cursor styles also seem to be working as intended. Alright, that's pretty much it for this video. But before we end, let's see what we can do with what we have right now. And we actually can do some neat retro style animations. So let's write some code to do that. And that's what the result looks like. And I think, I don't know, that's just nice. I like it. I really like it.
Yeah, that was quite something. And we barely scratched the surface. But there's this saying in my home country, mühsam ernährt sich das Eichhörnchen, which basically means that a lot of small steps and a little patience eventually lead to success. And we need to take that to heart. In part 2, we will take care of getting input from the keyboard. And until then, stay well behaved and keep it together or whatever. See ya.